It's my great pleasure to introduce Juan Esteban to the audience. He is a PhD student of the lab working on PINNs, so physics-informed neural nets, or other PDE problems related to that. And yeah, of course, so this talk is also, of course, intended to reach out to all the other collaborators and labs, and we all invite you to warmly follow up the talk and discuss this also after that. And I guess with that, I just hand over to Juan and looking forward for enjoying the talk.
So where should I put my camera? Yeah, maybe. Okay, hello everyone. Thanks for coming today to the talk. Hello everyone, my name is Juan Esteban, for the ones who doesn't know me. I'm going to present this talk that is called Learning PDEs by Convex Optimization for Polynomial Surrogates of General Sobolev Space. This is some work that has been done with Phil Hofmann, that is a master student here at CASUS. He's doing his master thesis and has contributed in several ways, theoretical wise, and also like in the framework implementation. So this is, let's say, a joint work that I will present here. And we are all part of Hecht's lab at CASUS. Okay, so let's start. What is this polynomial surrogate about? Let me first start by introducing like the general problem that we want to solve. So we want to solve a PDE in this general way. So we have a time dependent, for example, in this case of PDEs, we have time derivatives that not necessarily have to be the first time derivative. It could be in general any operator in time space, let's say. And here we have a nonlinear operator or a linear operator regarding the spatial, let's say, domain. So typically you would have here second derivative with respect to x or with respect to y and so on. So the thing that we want to solve this PDE, that here in this case we put this parameter lambda because the PDE could be parameterized by for example, I don't know, the viscosity or some constant that in some cases we want to infer. In some other cases we already know, so we just plug into the equation and we want to find the solution U. In general, we need some I don't know, well posed initial and boundary conditions to guarantee that the solution is unique and that the PDE is solvable. But well, we have in this general sense some PDE that we want to solve. Now, the way in which we are going to solve this is that we are going to take some surrogate model that will approximate the solution. Then, in particular, in this talk, I'm going to talk about two different surrogates. So first is neural networks as a surrogate, and the second one is polynomials as a surrogate. Now, in the case of the neural networks, we have the neural networks, they have some parameters theta, and the idea is we want to find the optimal parameters theta such that some loss that I will talk about in a minute is minimized. In the case of the polynomial, we can formulate in a similar way the optimization problem. Now, what are these three losses that we introduce here? We have the boundary loss, that is this LB, you see here. We have the initial condition loss in case the PDE is time dependent. And then we have the residual loss that is typically what denotes the PDE loss. So the PDE itself is included as a soft constraint in the optimization problem. Now we want to find the optimal parameters of this optimization problem. Now, in general, it's important to remark that these losses, they could be any well-defined metric. They doesn't necessarily have to be like the MSE error, that is the one that is typically used. But it could be extended to more general ones. So in particular, here we will deal with L2 norms. MSE is an approximation of an L2 norm. And we will also work with more general metrics such as the Sobolev norms, positive and negative Sobolev norms. Okay, so we have already the problem framed. Is there a question? Okay. Let me first put some motivating examples with our method. So the core method that I want to sell here is the polynomial surrogate as approximation of the solution. So the first result that we showed were done with polynomial surrogates for solving the variational problem. So here we have the 1D Poisson equation with some right-hand side that has a hyperbolic tangent. And then as you can see, the solution could have a very steep transition at the center of the domain, which makes it more or less difficult to solve. So what I'm showing here is the following: we can solve with the PINNs and with the polynomial surrogate and so on, the 1D Poisson equation for one fixed parameter beta. We can now change the parameter beta and solve again the PDE. Now, imagine that we want to obtain the solution over all the domain for a whole spectrum of parameters beta. So we want to learn a continuous function that will tell me at each position x and at each parameter beta what is the solution. So this is what we managed to do here. We at the end we recover a continuous model that will give you with these two coordinates what is the solution of the PDE. And it basically what it does is it solves with the variational formulation of the PDE each of the solutions for different beta, and then it interpolates into the across beta and across x. Then the result that we see here is errors of so the L1 error order of -6, and an infinity error is order of -4, the error, and like performing this whole computation just takes 16 seconds with our method. With PINNs, with neural networks, you will see in a moment how much more it costs. But this is just like to introduce one of the capabilities that the method has. So it can very quickly get very accurate solutions for the whole spectrum of a parameter. We have here another motivating example that is also difficult problem to solve, the quantum harmonic oscillator. So we present here for lambda equals 21. And then here we could see the order of magnitude of the errors. I will in a moment.
Eigenvalue problem.
This is the eigenvalue problem. Yeah. Exactly, eigenvalue problem with linear potential. So I will tell in a moment what these both methods mean, but they are both polynomial surrogates. And as you could see that we are reaching errors of 10 to the power of -9 in just 6 seconds with this method here, and 10 to the power of -3 in 57 seconds. It's still quite good compared to PINNs because they failed to recover this solution. So yeah, so this is just to motivate like where we are going to reach in the talk. And now I will go a little bit in the detail into the theory, let's say, on how the method works. So let me first talk very briefly about Sobolev spaces for the people that are not so familiar with this concept. So in general, Sobolev spaces are generalization of L2 Lebesgue spaces. So in particular, H0 space is just the L2 space. So all the functions that are L2 integrable. So you square the function, integrate it over the domain, and then this has to be bounded. And then we can define the case Sobolev space as all the functions that belongs to L2 and that its derivative belongs to L2. This alpha is a multi-index denoting dx, dy, dx, dy, dz, and so on. So all the possible combination for the derivative. And then this is how we can define the case Sobolev space. Now, the Sobolev space, we can equip it with a norm, and then the norm will be the L2 norm always. We require this for this HK norm to be a norm and not a semi-norm. And then the sum over the L2 norms of the derivatives. Now, for our method, it is very important to also introduce negative order Sobolev spaces. So this is like one of the key in the performance of our method. We really used it very intensively, and yeah, kind of the performance of the method relies on using this kind of spaces. So we will define the negative order. Wait, the case order, sorry, yeah. So the H minus K norm, we will define it as the supremum over all the functions in HK of some f, some functional f applied to u divided over the norm in HK of u. Now, what are these f? So f is a distribution, so an element of the distribution space, which is the dual of all the smooth test functions with zero boundary conditions. Yeah. So I think I will not go more into detail regarding this norm at this point. In a moment later, if someone has a question or if we have enough time, then Phil can come and talk much more about
the short comment. So f could be, for instance, integrating u times a certain fixed function.
Yeah. So it's a linear functional from the space of
given intuition.
Into the real, yeah.
Sorry for that.
No, it's fine. Thanks for the clarification. So yeah, so these are the norms that we are going to deal with in this talk, and that will help us to compute, in particular, the losses. Yeah, so it does affect if we choose the L2 norm or the H1 norm or the H2 norm and so on, as we will see. Okay. Now, we are going to talk about the PDE formulation and how to formulate the residual losses in particular. So let's put as an example the Poisson equation with the Dirichlet boundary condition. So we have the classic formulation of what we denote here by strong formulation of the Poisson equation. So we have minus Laplacian u equals to f in the domain, and then we have the boundary conditions equal to g in the boundary, of course. Now, we can weak a little bit the notion of this PDE by, for example, testing with a test function phi, with a smooth function phi, and integrating over the whole domain. Here, the regularity of the solution is still the same, so we are not decreasing the regularity in terms of the derivative. We still need to compute second derivative. Here, in this case, it will be second order weak derivatives. But it's still a weaker notion than the strong formulation that we have here. And then we have that this has to be fulfilled for all the smooth functions phi into infinity. Again, we also need to guarantee that the boundary conditions are fulfilled. Now, using this same formulation, equation 8, we can now use the integration by parts, and then we will pass some of the derivative to the test function, and now we will have an equation that requires less regularity in the solution. So instead of being H2, like in this case, it will be H1. So we just need the first weak derivative, and then the other derivatives are going to be like transferred to the test function. Now we can do this trick twice, and then you will not need any derivative at all on the function u. But so this is just to give a notion of what we can do with the PDE formulation. We can have a strong formulation, what we denote by strong variational formulation, and what we denote by the weak variational formulation. And now the key problem is how to formulate losses with all these three formulations, no? Because this is what is important for us, to formulate losses that then we are going to minimize. Also, let me remark that in practice, we don't solve over the whole space of smooth test functions, but we just solve over a finite dimensional polynomial space. And then we require that the equation is fulfilled for all the Lagrange spaces, which implies that it will be fulfilled for all the polynomial space. So now I will introduce how these residual losses look like. So for the strong formulas, the strong Sobolev loss, we can define just as the residual minus the Laplacian u minus f in some HK norm. So it could be L2, H1, H minus 1, and so on. But then here the key is that we first compute the residual, we square the residual, and then we integrate over the whole domain. Now we can define the strong variational loss, that is the residual, again, tested with the Lagrange spaces, integrated, and then squared. So the difference between equation 10 and equation 11 is that in equation 10, we first square the function, and then we integrate. In equation 11, we first integrate, and then we square it. Yeah, and then this has like the big property that with equation 11, we can reach to equation 12, that is the weak variational formulation, and we can do integration by parts. If we first square the function and then we integrate, it's not so clear how we can do this trick of passing the derivatives into test functions. Yeah. So with this, we can have three different kinds of losses that we could use for our training. And actually, in many of the experiments, we tested with a strong Sobolev loss, with a strong variational, and in some cases with weak variational, but we mainly focus on a strong Sobolev loss and a strong variational loss. Okay, I will not go that much into detail into this section, but this is just to leave the message that of course, in the neural network setting, and also for our case, for the polynomial surrogates, the way in which we are going to find the optimal parameters is by solving this ODE. Yeah, there is a gradient flow of the parameters theta with respect to the loss. In practice, this is the same as performing the gradient descent. So the gradient descent is a discretization, it's a discretized solution of this continuous ODE in time. Yes. And then another important thing is that the gradient of the loss will depend on which metric we choose, which metric in a finite dimensional space. So depending which metric, we could have different kind of gradient that will perform in different way. So in particular, we have a way in which we can compute L2 gradients. Of course, this is just the typical one, but we can also compute Sobolev gradients. During this whole implementation, we observed that the L2 gradients were the ones that were performing the best. So we will restrict in this case to just L2 gradients. But anyways, we could have L2 gradient flows, but change the metric in the finite dimensional space, and this will have different properties. Yeah, so at the end I could give more details like in this theoretical part. I think it's not so relevant for now. Just want to show you that equation 14 is the gradient flow for the strong Sobolev loss, and equation 15 is the gradients for the strong variational loss. So as you can see, the only difference between both formulations is just some W squared, which might have some numerical properties comparing one with another. So yeah, let me continue. Okay, so I will talk now a little bit about the physics for neural networks and like its properties. So in the settings of PINNs, what is called PINNs, we consider a neural network as a surrogate model of the solution of the PDE, right? Now, choosing neural networks as surrogate has a problem that the optimization problem itself at the end is a highly non-convex, non-linear problem, even though the functionals are convex. So we are usually dealing with L2 integrals or H1 and so on. This could be convex, but the problem itself is not convex because the dependence of the neural network with respect to the parameters is non-convex. So this makes it very difficult to solve, and then we might fail into these problems of just arriving to local minima, getting stuck into local minima. It's not clear how to guarantee that this will converge to the solution of the PDE, which is very important, of course. Or to which solution. It can be that you converge to a lower energy solution, depending on the optimization problem. Now, one big issue that the PINNs have in general is that they are not robust against loss imbalances. So as I showed at the beginning, we have the PDE loss, we have the boundary loss, and we have the initial condition loss. So in many cases, not always, we can characterize in which cases, but in many cases, the PDE loss has bigger magnitude than the L2 loss. So if you take the derivative, take the norm of this will have bigger magnitudes. Just the semi-norm terms, so just the term regarding the derivatives. This will have bigger norm than just, for example, the L2 norm. And then this will create an imbalance in the loss of the PDE, an imbalance in the loss of the boundary condition, for example. And this could cause two things. First, that you converge to a local minima in one of the losses and not in the other. So for example, if you converge in a local minima of the PDE, it could be that it's not the minima that fulfills the boundary conditions. So you are not getting the solution that you expect to get, right? So this is a very, very critical problem. And the second one is that you could get instabilities during training. So actually the loss could explode to infinity due to these imbalances. So in general, it's not robust against this, and this is a phenomenon called numerical stiffness. Also the additional problem that we have high number of parameters to be optimized. So a lot of neurons, a lot of layers, and then the cardinality of this set will be very high compared to the other method that I will show you. And just to say that we have one first paper that we submitted to the ICML conference, is still under revision. But basically what we do is that we take the PINNs, so the typical neural network for solving these PDEs, and then we replace the MSE loss with something that we call Sobolev cubatures. So we approximate the neural network by polynomials, and then we compute the integrals exactly of the polynomials. And then at the end, we replace MSE losses by just weighted sums on the Legendre grid. Yes? So this is the Sobolev cubature PINNs approach that replaces MSE for Gauss-Legendre quadratures. And we observed that it performed better than all the benchmarks that we did. Also, some specialized methods that were designed to balance the losses, we perform better in the experiments that we perform. So this is like, let's say, the state so far regarding PINNs and the quadratures. Now, I'm going to introduce the important method, let's say, and just let me give a brief intuition about what is happening. So yeah, let's see. In general, for the PINNs, we have some physical domain, right? We have some data, that is the training data that we're going to feed into the neural network. We pass it through the neural network, and then we obtain the solution so the neural network, this is parameterized by theta, at the training points X, right? If it's the MSE, then this is going to be randomly sample points, or it could be, whatever points you want. And then with these points, you pass it the loss, and then compute the gradient descent, right? In the case of the Sobolev cubature pins, we have now not any grid, but we specifically need the Legendre grid. We pass it through the neural network, and then we will obtain the function evaluated at the Legendre grid. Yeah, and the same, we will pass it to the loss to be computed, and then do the gradient descent. Now, but if you see this function evaluates the Legendre nodes, this is nothing else than the coefficients of the Legendre expansion of a polynomial. So that means that if you have a polynomial qx, we can expand it as some coefficients. So sorry, so multi-index C alpha, L alpha. So these coefficients are just the function evaluated at the Legendre grid. Yeah. So if we stay for a moment and look at the problem, we can formulate, or we can generally frame the Sobolev cubature approach as the following. We have some domain, we have some Legendre grid, and then we are actually just using a nonlinear map between the domain and the Legendre coefficient. So this is all what the neural network is doing. So like in the PINN's approach, the neural network is like the main part, right? It's like the core of the whole approach. But if we think about it, we are just using it for a little part that is approximating a nonlinear map between the physical domain and the Legendre coefficients. That is what we denote here by this eta. So the natural question is, why do we need neural networks? If we are already in polynomial space, so all these from here to there, we are already in polynomial space, right? So why do we need neural networks? Now, it's not clear that the complexity of the neural networks will not help to the approach. But as we see in the experiments, and let's say with the theoretical properties, replacing the neural networks by just polynomials brings several advantages. And then this is what I will present here. So one thing I need to... 1 second, sorry. Yeah. So now let's go to the polynomial surrogate models. So instead of choosing neural networks as surrogates for approximating the PDE solution, we choose Chebyshev polynomials. Chebyshev polynomials were the ones that perform the best, so this is why we chose this. And then we will use Chebyshev polynomials as the surrogate model, but still the Legendre grid for computing the losses and so on will remain the same. So the only part changing there is just which surrogate, which model we are using for approximating the solution. Now, the big properties that doing this change, let's say in the concept of the method brings, is that as soon as we choose polynomials instead of neural networks, then the polynomials are linear with respect to the coefficients, and then the whole optimization problem will become convex with respect to the coefficients. Yes, it will become strictly convex if the solution of the PDE is unique, for example, but in general it's convex. So this is the first big advantage. Then the second one, as I put in the second remark here, if we assume that the PDE is solvable and is unique, the solution, then okay, we also need that we also require that we have a coercive loss, but all the losses that I introduced you before, they are coercive. And we have these three conditions, then the variational problem, so the optimization problem, has a unique solution. So the solution exists and is unique, just by exploiting this property or this structure of the polynomials, let's say. And then this means that we can find the optimal parameters theta at convergence for a fixed degree n. This is what the uniqueness implies. Yeah.
And the parameter theta is just multiplying each term of a polynomial of the Chebyshev.
So exactly. So
scalar number multiplying.
So the parameter, so the zero parameter will be this parameter multiplying the basis 0. The first component will be the first component multiplying the first basis. So yeah, it will be just linear combination.
Okay.
Yeah. Okay. Then this is why, yeah, precisely is linear with respect to the parameters. Okay. Now, if we just restrict to linear PDEs, we can write the finite dimensional gradient flow. So finite dimensional in space, but still continuous in time. We can write it in this way. Now, what is important from here that I want you to, like the message that I want you to stay, and is that this problem is just an affine map applied to the parameter theta. And then the solution for this ODE is known. And in particular, we can also find the analytic solution of the gradient if we just yeah, 1 second. Okay, this is not a good idea doing these changes. But well, if we just So we have that the gradient flow is something like this. So matrix X plus B. So this is why it's an affine map. Well, here's theta, sorry. Then in particular, we can also find the solution, right? We just impose that this is 0, and then we can just solve the linear system of equation by inverting this matrix. Now the key property here is that this matrix is positive definite and is symmetric. So it's not so bad behaved, let's say. And many of the experiments that we performed here were solved by just inverting this matrix. And this gives like huge time performance and also accuracy performance. Now for more general cases in which we could not invert this matrix because it's too big, or in general it could be ill-conditioned, or we are in a nonlinear PDE setting, then we use the typical, or let's say the framework that I described before with the neural networks and just perform the gradient descent. In that sense, will be the same. Then one last remark regarding this. So the properties for linear PDEs is that in case we want to solve the gradient descent for a linear PDE, then we have exponential rate of convergence. But now this is not only for linear PDEs, but for any PDE that makes the convex lambda uniformly convex. So meaning that if we take the Hessian of the functional, then this will be lower bounded by lambda and then the identity. So it's like a uniform lower bound for the convexity of the functional. Then if we have this property, then we can also guarantee exponential convergence to the rate lambda. So it's not only restricted for linear functional, but all the functional that make the loss lambda convex. So this gives like a lot of hope for extending to more difficult nonlinear PDEs, for example. Okay, now let's go to the numerical results. So we know those nice properties. So going back again, this was solved by using the polynomial surrogate model. And then just to give like a little comparison, the PINN, the normal PINN, if I'm not wrong, for solving this problem, takes something like 200 seconds for solving one. Now what we do here is that we take so we take beta, we sample Legendre points. So they're not equidistant, but they follow, like, let's say, the Legendre distribution. And then we solve for each parameter beta. Now we have all the points for interpolating with respect to beta. And this is what we do. So performing all these with 90 PDEs, yeah, for 90 different betas, it took only 16 seconds, the whole method. For PINN, it takes 200, just one PDE. So I mean, the difference is huge. And this was solved by using what we did denote by analytical gradient. So solving analytical, so inverting this matrix. And again, we have gradient flow, polynomial surrogate. So it performs worse than the analytic one. It's still quite fast if you compare it to normal PINNs. So the best one is analytical, but of course the analytical is limited in its application. So it's like the limit case that we can reach with the gradient flow in some sense.
So what is the difference? I didn't get quite the difference between. So the first one is gradient flow, second is analytical. Is that
analytical. So the analytical is the one that we use, that in which we solve this linear system of equations. So you put here equal to 0, and then you solve the parameters theta. That makes
analytically or numerically.
I mean, yeah, in this case numerically, but it's the analytical.
Just relies on matrix inversion.
Yeah.
You do, okay.
And then as soon as you have inverted matrix, you just more or less have the solution.
Yeah, exactly.
And the other one really follows the solution by following the matrix as a gradient descent.
So if you cannot afford to invert the matrix, you would do the gradient flow.
Exactly. And also for nonlinear, no? Because if this equation is nonlinear or polynomial, and then first what is the solution of the ODE? And so you cannot obtain it analytically.
You should solve a nonlinear system of equations.
Exactly, or you should solve a nonlinear system of equations, which is very expensive.
Yeah, of course.
But you have guarantees for the convergence in the gradient flow problem too? That
it's the same, I mean up to numerical error in the discrete. So because the gradient descent is just a discretization in this scheme, right? In equation 17. So up to the errors of discretizing this equation, then you can guarantee that the solution exists and is unique. So of course, if the time integration, that is what is denoted these ODE solvers, is unstable, for example, then you will not reach the solution. But then this is where the additional error of the numerical approximation of the solution of the ODE comes in. But then, I mean, in theory, if you can guarantee that the time integration is well known, then you can guarantee that you will converge to the solution.
You just have to apply a gradient descent method to a convex problem, which up to numerical issues is always unique or converges.
And you can really see it in the plots of the losses, it converges exponentially fast.
Yeah, it's really interesting. And so does, and the matrix here, the matrix is K, right?
So the one that we want to invert is K star K.
K star K.
That it includes the adjoint operators of the differential.
So all these complicated gradient formulas, which were previously somehow condensed in this matrix K.
Exactly. So
What, I'm just curious, what determines its dimension? So what parameter of my problem determines the dimension of that matrix I need to invert?
the number of Legendre points, so the degree of the polynomial. So if you see here, the K star is hidden here. So you could denote it by the second derivative transpose times W in this case, for example.
In that sense, it's the domain. So
it's the domain times the domain.
No. It's a choice or a
choice of.
So the Legendre nodes scale, unfortunately, exponentially with dimension. But the degree is reasonable low. So if you have degree 30 in dimension 3, it's 30 to the 3, which is still reasonable to do as a matrix linear computations, right?
But this domain is the domain, the parameter domain.
No, it's the physical domain.
The physical domain.
Yeah.
A physical 3D problem needs matrices of size, let's say 30 to the 3, which is somehow less than 3,000 size of the matrix. 3,000 times 3,000, let's say, like that's doable.
Doable, right? Yeah.
So it will also be affected by the size of your basis space, right?
Sorry?
It will also be affected by the size of your basis space, right? Or
yeah, but I will say it's determined by the degree of the polynomial at the end. So even if you're in Legendre with Lagrange basis, and then you switch to canonical basis, the degree of the polynomial is the one that determines the size.
Can I say one thing for this? Yeah. So the thing is, so when we discretize something and we have this Legendre grid, then it seems for at least the linear PDEs to be optimal to choose the highest degree. So somehow, in some sense, of course, the degree of the polynomials are bounded by the number of points we take. And for example, for linear PDEs, it's the same. So we take same degree, same points, and this seems to be optimal. So
yeah, so to clarify that a little bit, it's just that we could have two different degrees in the whole system. So we have one for the surrogate. So this belongs to some PS, let's say, and then we have one for computing the quadratures. Yeah, so I don't know how to denote this, but well, we have one for the quadratures, and they don't necessarily have to be the same. Yeah, so the ones that you use for integrating doesn't necessarily have to be the same that the ones that you use for approximating the solution itself. But what we have seen that we were with our approach, if we choose the same degree for the polynomial, so for the Chebyshev polynomial, and the same degree for computing the integrals, yeah, so this. For computing this, P alpha square, for example. If the size of this is the same as the size of the cardinality of the points of the surrogate, then it performs the best. So this is what Phil is referring by that. So we could have two different degrees. But in general, these matrices correspond to the degree of the quadrature, so of the integral that we want to compute.
How does as the complexity of the problem is also theta, the parameters, how does that affect?
Yeah, that's what we said. So the degree for the polynomial surrogate model determines how much theta, how many coefficients in the Chebyshev surrogate.
Yeah, of course.
And the degree of let's say regularizing the whole thing, how good do we want to approximate the real loss, is the degree you can choose for which quadrature rule you apply. And in principle, you could differ them, and what Juan tried to explain, if you take them equally, it seems to perform best. But in principle, there is still freedom in that. And these determine, in the end, the matrices which occur there.
So in general, the model looks like this, no? So it's a sum over the theta I, the parameter we want to learn, and the Chebyshev basis.
Okay, yeah, I see.
It's like choosing more layers for the neural net would be the same concept would be the degree of the polynomial surrogate. And let's say choosing the batch size for taking the MSE loss, right, would correspond to taking the degree for the cubital rule.
Exactly. This is a good analogy.
And then you can, as usual, you can play around with these.
So here I have some comparisons between, so not the standard pins, because I mean, this already, let's say, is shown in the first paper that they perform worst, but now we compare our polynomial surrogate to the Sobolev QH pin that is already performing best than the normal pins. And then here we could see the big difference. I mean, in runtime using GPU, we need 477 seconds for obtaining solutions up to 10 to the power minus 4 and L infinity 10 to the power minus 3. And as soon as we go to the polynomial surrogates, we get twice. So 2 orders of magnitude better accuracy, and the time is just 2 seconds.
What is epsilon infinity?
So the infinity error. So just taking all the points and taking the maximum. So absolute value of the error.
The worst errors you see on the maximum error.
You have your neural network, let's say, you subtract the ground truth on the testing points. And then you say, give me so take the absolute value of this, and you say, give me the maximum error there.
Okay.
So it's the biggest error between
Error in
the solution and the ground truth.
And here you're looking at which state? Oh, 31.
Yeah.
31. Okay. Got it.
Exactly.
Just notation.
And epsilon 1 is just summing them all up, all errors.
Okay.
And now, if we go to the analytic solution, then it's already 10 to the power minus 14 in 1 second, so even less time. I mean, exploiting the fact that this is linear PDE. We have also experiments for the 2D Poisson equation, so a lot of modes, so we have very high frequency. And then the same, we see, well, here we include the inverse Dirichlet thing, that this inverse Dirichlet is a method for balancing the losses, and it helps improving the training for normal pins with MSE losses. But then we can see that first, the Sobolev QH pin perform better in this case, in half the time. But now if we go to polynomial surrogates, then again, 2 orders of magnitude increase in accuracy, and then the time is just.
And you should maybe mention that classic pin approaches cannot solve such problems.
Classic pin approaches, in some cases, they cannot solve. So they are very sensible to this stiffness problem, and then it could be that it converges to a wrong solution. So yeah, and then here this star denotes, I mean, means that we just increase the number of points to 200, if I'm not wrong, and then we reach 10 to the power minus 14. So we can reach very high accuracy by using just these polynomial surrogates. We have this function that is very oscillating, let's say, so it's a difficult function, it has big oscillations, and it has this very hard transition at the center. And then again, we can get with the gradient flow or with the gradient descent, 10 to the power minus 4 in 44 seconds, and with the analytical one, 10 to the power minus 10. So yeah, so the results with the analytic one are very good in general, also for complex functions. Okay, I think I will stop here. I just want to say that yesterday that we were like preparing the response for the Sobolev QH pins. We performed 2D Poisson equation, and it still performed better than the normal one. And we can get the solution with polynomial degree 20 in 3D and polynomial degree 30 for the boundaries. So it also gives lights that we can scale the problem to higher dimensions. And with the Sobolev QHs, with the Sobolev pins, sorry. With the polynomial surrogates furthermore, of course, as we can see here the times. So yeah, I don't know if Phil wants to say something. Maybe do you want me to show the slides of the negative Sobolev norm? Or
If there's some interest, I can do this, of course. I mean,
okay, then maybe let's leave it for the questions. Maybe I will just say.
yeah, so maybe first answering some questions if there are some.
Yeah. I will just say some possible further steps that this method have. is basically now trying to solve inverse problems. We can also do it because it has the same flexibility as the PINNs. So trying to estimate the parameter lambda, for example, on the Poisson equation or in any other equation. This domain decomposition is a work in progress that if someone else is interested on this field could describe. So basically we can decompose the domain, find the optimal size of this domain, and then solve the whole variational problem. Yeah, well, I think we'll not go much more into details here. Yeah, I think this is all for now, and then I think questions will help more. Yeah.
Okay. With that, I would say we thank Juan.